Hello everyone, my name is Abhinav Kumar and I'm an undergraduate student at St. Louis University. Today I'm presenting SCLERA, a framework for privacy preserving machine learning as a service at the pervasive edge. This work is a collaboration between St. Louis University and Intel Labs, and it's partially funded by Intel Labs. Due to the increase in volume and demand of latency-sensitive application, due to vehicular networks, IoTs, and image analytics, edge computing has seen significant growth. It is estimated that by the year 2026, more than 50% of the enterprise data will be generated at the edge. It is also estimated that by the same year, the edge computing market would be worth more than 10 billion US dollars. Computer vision and machine learning as a service are one of the most important use cases at the edge, both of which have revolutionized multiple industries. Computer vision market as of now is worth more than thousands of millions of US dollars. There have been multiple proposed ecosystems for the edge, pervasive edge computing ecosystem being one of them. The pervasive edge computing ecosystem benefits from inclusion of user-owned devices in the existing edge infrastructure. This gives us a bigger pool of heterogeneous computational resources, allowing us to better utilize the computational resources present at the edge. There are multiple security vulnerabilities that exist in both training and deployment of neural networks. For example, in the training phase, there could be data poisoning attack and transfer learning attacks, where the attacker tries to modify the decision boundary learned by the model. Or it also tries to install a backdoor to the neural network, which it can exploit later on. In the inference phase, there could be attacks like privacy inference attack, physical attacks, or evasion attacks. In physical attacks and evasion attacks, the attacker tries to affect the accuracy of the model, leading to inaccurate predictions. In privacy inference attack, it tries to either attack the input provided by the user or the dataset the model was trained on. This work focuses on privacy inference attacks. There are three prominent privacy inference attacks: membership inference attack, property inference attack, and input reconstruction attack. Membership inference attack and property inference attack both target the dataset on which the model was trained on. Membership inference attack tries to infer whether a given image was part of the training dataset or not. And property inference attack tries to infer whether a certain property was true for the training dataset or a subset of images in the training dataset or not. In input reconstruction attack, the attacker looks at the smashed data coming out of a submodel or the output of an intermediate layer and tries to reconstruct the input given by the user. There have been multiple proposed solutions to avoid these attacks, such as homomorphic encryption. Homomorphic encryption allows you to do computation on encrypted data. However, it's extremely slow and could be computationally expensive. It takes up to 970 seconds to run a single inference using Resident 50. Modern homomorphic encryption schemes such as CKKS can also cause a reduction in accuracy of your model. There have been many proposed solutions using trusted execution environment. However, low-range Xeon models and AMD TrustZone have limited EPCs or enclave paging cache. There have been workarounds to this, such as running linear layers outside the trusted execution environment using string ciphers and non-linear layers inside the trusted execution environment. However, that would require high amounts of precomputes, which could get really expensive, and the solution is also not scalable during the training phase. That also requires expensive hardware such as high-speed SSDs to make the solution viable. Other proposed solution using trusted execution environment includes running initial layer outside the trusted execution environment and later layers inside the trusted execution environment on the same untrusted machine. This can protect your model from membership inference attacks, but it does not protect it against input reconstruction attacks. SCLERA solves the previously discussed problem with a 4-stage pipelining, optimization, and compression framework. First, it allows the user to take their existing solution, such as a pre-trained, fine-tuned, or a model trained from scratch, and use the on-demand model splitting library to deploy it in a privacy-aware system. This is a very powerful industrial tool, since now the developers do not have to think or even take in consideration any pipeline or distributed framework while training their model. They can take their existing solutions and deploy it in a privacy-aware framework. Next, we use quantization or dynamic range quantization to convert the weights and activation to 8-bit integers. This allows us to significantly reduce the memory footprint of the model and minimize the paging caused in the enclave. Then we use enclave parallelization to amortize the cost of enclave creation and loading time, which could become a significant overhead if you are using a stream of data and could add up over time. SCLERA also features a resource-aware workload offloading policy for video inferencing. Instead of sending all the frames for inferencing, we only send a subset of frames. And the subset of frames are not selected randomly, since that would cause a reduction in accuracy. The subset of frames are selected based upon the amount of contents present in each frame. For example, iframes have the highest amount of unique content, therefore they are always sent for inferencing. However, p frames and b frames have less amount of unique content, and they are sent less frequently based on the use case mentioned by the developer. All of these components together make SCLERA. So let's see all of these components in one picture. First, the offloading policy selects the frames required for inferencing, then send it to the submodel running on client's device. The client's device encrypts the smashed data coming out of the submodel and sends it to the enclaves running on the Pervasive edge server. And then it uses remote attestation to verify the enclaves running on the Pervasive edge server. The Pervasive edge server, in their trusted execution environment, runs the second half of the model and returns the output back to the client device. Now let's talk about the experimental setup. The experimental setup consists of a Ryzen 5 CPU with 8 GB of RAM on the client device and an Intel Xeon CPU with 16 GB of RAM and SGX support on the server side. The three tested models are ResNet 50, ResNet 101, and VG16, all of which were pre-trained on ImageNet dataset. First, we tested how many blocks of a certain neural network could be run inside the trusted execution environment without causing significant paging. The x-axis shows the number of blocks running inside the trusted execution environment, and the y-axis shows the inference time. Running 3 to 4 blocks inside the trusted execution environment for ResNet 50, ResNet 101, and VGG16 gave decent results and close to real-time performance. However, running the fifth block for VGG16 caused significant increase in inference time due to an increase in paging. This made us realize that we should test most of the given models, such as ResNet 50, 101, or VG16, on a split where the first two blocks would run outside the trusted execution environment, and the later 3 blocks would run inside the trusted execution environment. After using the split shown in the previous slide, we tested these 3 models and came with these inference speeds. For ResNet 50 and ResNet 101, SCLERA reached close to bare metal performance. For VG16, where SCLERA did not achieve close to bare metal performance, it provided a significant improvement over the base case, which was running the complete model inside the enclave, making those bigger models more usable for a lot of use cases. A specific point where SCLERA shines is reduction of overhead. The overhead consists of enclave creation time, loading time, and memory paging. In parallel workloads, SCLERA's pipeline can cost 25 times reduction in overhead. If you have a sequential workload which cannot benefit from the parallelization of enclave, SCLERA can still give you around 6 times reduction in overhead, which is a significant speed up. After the optimizations shown in previous steps, SCLERA uses the offloading policy to achieve close to real-time performance for image labeling use cases. The x-axis here shows the compression rate. 100% compression rate stands for sending only iframes for inferencing, whereas 0% compression rate stands for sending all the frames for inferencing. Any frame in between is the rate at which P or B frames are set for inferencing. For example, if you have an image labeling use case which does not care about the position of the object, you can only send iframes for inferencing and you would get high accuracy. But besides, if you also care about the position of the objects present inside the frame, you may also need to send P frames and B frames slightly more frequently. At 100% compression rate, SCLERA can do inference on a 10-second clip in around 10 seconds. Even for other compression rates, SCLERA outperforms the base case of completely running the model inside the enclave significantly. So what are the key takeaways? Existing solutions are either not suitable for edge deployment or consider a simple adversarial model. SCLERA provides a privacy-aware framework for offloading continuous deep learning workloads to the pervasive edge. It offers a pipeline for on-demand model splitting, quantization, and parallelization, which drastically reduces the inference latency between 6 to 23 times when compared to baseline schemes. For models like Resonant 50 and Resonant 101, it achieves close to real-time performance. In future, we plan to extend SCLERA for model training and fine-tuning. We also plan to optimize the framework for running parallel enclaves across multiple servers so that more compute-intensive applications could be tested. Thank you.